Well, let's have a look at Leading Cert 2008. Question number 9 from the physics paper. This is a full 56-mark question from Section B, and you should spend no more than 20 minutes approximately doing this question. This is a really nice question. There's great imagination in this question, where you've got to bring your physics together in a very, very unfamiliar kind of way. So you have to do a little bit of thinking. It starts off nice and traditional, so let's have a look at it from your notes. It says to me, what's meant by the refraction of light? You know that definition, don't you? We're talking about light bending or changing direction. When it moves into a medium where its speed changes. They're the 2 points I have to make. And then state Snell's law of refraction. You can write that down as a formula. Sin I over sin r is equal to a constant. But make sure you put the notation in as well. So let's have a look at this on the board. So refraction of light for 6 marks. Get in, refraction is the changing in direction of light as it enters a region where its speed changes. They're the 2 points I need to make. So it'll be 6 altogether. It'll be 3 for the change in direction and 3 for the speed changing. And then they're asking me to state Snell's law. Well, you can use your formula. Because when you look in your summary, or your notes, there's an asterisk beside Snell's law definition. So you can write it down as a formula that's in your table book. You can write down that sin I over sin r is equal to a constant. Or in the table book, that constant is written down as n. Now, you'll get 3 marks for writing down the correct formula. But you've also got to put in the notation. What do the letters stand for? So I stands for the angle of incidence, and R stands for the angle of refraction. But if you just write it down as n, you'll probably write down that n is the refractive index. So 3 for the formula, and 3 for the notation, as we call it. Anyway, that's straightforward, that's standard. Now I get into the intelligent part of the question, the really interesting part of the question. So it tells me that an eye consists of a lens system and a retina. The retina is 2 centimeters from the lens system. Your retina is actually the screen. So the image distance, V, is 2 centimeters. It'll be plus as well because the image has to be real. A real image has to fall on your retina. The lens system consists of a cornea. That's the window at the front of your eye, and all the jelly behind it would be part of this lens system, which acts as a fixed lens of power 38 per meter. You can't change that value. And we have this internal lens, which is variable behind the cornea. The maximum power of the eye is 64 per meter. That's when your eye is working at its hardest. It's at its thickest. That's when you're looking at near objects. They're asking me in part 1 how near an object can be placed. So we can still see that object in focus. That's called my near point. And they're asking for the maximum power of the internal lens. So 15 marks for all that. So let me look at that in detail, because that is a little bit tricky, what we're talking about there. So I've actually tried to put a little diagram together so we can actually visualize it. So we have our cornea and probably the jelly stuff behind it. That's a fixed lens. We'll call that lens number 1, and the power of that is 38 per meter. Then behind that, we have our variable lens, whose shape we can change. So we'll call that power 2, lens number 2. That power can change as you're looking at distant objects and you're looking at near objects. There's my retina, and it's 2 centimeters behind my lens system. So the image distance V is 2 centimeters. They're telling me the maximum power of the entire lens system, P max, is 64 per meter. And what they're asking me to do in part 1 is, how near can an object be placed? In other words, when my lens system is at its maximum power, what's the nearest object I can see and still be in focus? Well, I want to work out the focal length of my lens system when it's at its maximum power. So the first formula I write down is P is equal to 1 over F. That implies, slide the F up, F equals 1 over P. So we're talking about your maximum focal length. 1 over P is 1 over, what's my maximum power? 64 per meter. 1 over 64 per meter. I'm going to put the 1 over 64 into my calculator. And I get 0.0156. Bring the m to the power of minus 1 up, and it becomes meters. Then most of our problems when we use the lens formula is in centimeters. So let me turn that into centimeters by multiplying by 100. And I get 1.56 centimeters. That is the focus of my lens system when it's at its maximum power, when I'm looking at objects really close to me. Now I'm going to write down my lens formula. 1 over U plus 1 over V equals 1 over F. And I want to find the object distance when F is 1.56 centimeters. So fill in the numbers. 1 over U plus 1 over V. V, that image distance is fixed. That's 1 over 2 is equal to 1 over 1.56. So normally we do these questions manually. The numbers are a bit nasty. So let me use my calculator to do this. So I'm going to jump that half across. So it's going to be 1.56 minus a half is equal to 1 over U. And then we're going to turn both sides upside down. We're going to turn the U upside down to get the 1 over U upside down to get U. And to turn all this upside down, because of that minus, I'm going to wrap it in brackets and put it to the power of minus 1. That will turn it upside down for me. So I've shown you those calculations in the experiments. So let me put that into my calculator. Fraction, 1 over 1.56 minus a half, close bracket, all to the power of minus 1. And I get 78/11, which is about 7.1 centimeters. That is my near point. That's the nearest I can see an object that is still in focus with these eyes. Nice question. Now I move on to the next part. They're saying, what's the minimum power of my lens for 3 marks? Well, I'm going to use my other formula, which is P is equal to P1 plus P2. So P max is 64. That's the overall power of the lens. That's equal to P1, which we can't change. That's 38. Plus P2. So P2 is the power of my variable lens. And what is the minimum power? Well, P2 is equal to 64 minus 38. And that gives me 26 per meter. That's the minimum power of my variable lens. So let's continue with this question. So we're saying that light is refracted as it enters the cornea from the air as shown in the diagram. You've got our light, there's the incident ray in the air going into the cornea, refracted ray on the right. You've got to calculate the refractive index of the cornea. So let's have a look at that in detail on the board. So how do we do all refractive indices problems? They're nice and easy. We just set up our table. We have our 4-part formula. So what am I got here on the left? Air. So that goes top on the table. And then I've got the cornea. That goes bottom of the table. So the angle of incidence is in the first medium, and that's equal to 37 degrees. And the angle of refraction in the second medium, that's 27 degrees. Refractive index of air, we already know. We're going from air to air, so that's always 1. And the refractive index of the cornea, that's what we're asked to find. So I'm going to use 2 parts of my 4-part formula. I'm going to use the first part, I's and R's, and the last part. Remember, when you applied this last part, turn the refractive indices upside down. So what have I got? I've got sine I over sine R is equal to, turn them upside down, NC, the refractive index of the cornea, over the refractive index of air. Let me put my numbers in. So sine 37 degrees all over sine 27 degrees is equal to NC, which I'm looking for, divided by 1, which I can leave out. So let me do that calculation on my calculator. So fraction, sine 37, close bracket, scroll down to the bottom, all over sine 27 degrees, close bracket. That equals, what have I got? 1.325, let's say about 1.33 is what I've got. So my answer for NC is about 1.33. That's a simple calculation. You've done many of them already. So let me go on to the next part of the question. They're asking me to draw a diagram to show the path of a ray of light as it passes from water, whose refractive index is 1.33, into the cornea, whose refractive index we've just worked out. What is the refractive index? That refractive index is 1.33. But that's what I need to do. So let's have a look at that on the board. Well, here's water. Refractive index of water, NW, is 1.33. Here's the cornea. Refractive index of the cornea is about 1.33. So you're moving from one medium into another medium, but the refractive indices are exactly the same. So what does that mean? That means the ray of light is not going to bend. So let's say, I'm showing my diagram. So here's my incident ray going from water into the cornea. Well, when it goes into the cornea, it's not going to bend because they're going to be traveling at the same speed in each medium because they have the same refractive indices. So the important thing to show in your diagram is the ray of light does not bend. Let's continue my question. An interesting question. It's actually examining a lot of things, not an easy question either. So moving on. A swimmer cannot see properly when she opens her eyes underwater. When underwater, why does the cornea not act as a lens? Well, it's what we've already said in our diagram. Why does it not act as a lens? We've already said, when light goes from water into the cornea, because they have the same refractive indices and therefore the same speeds, the light doesn't bend. And that's what a lens does. A lens bends light. So if it doesn't bend, it's not acting as a lens. So what will I say for my answer? My answer will be, for 6 marks, light is not refracted, as water and the cornea have the same refractive index. So basically 6 marks, 3 for saying it's not refracted, and then 3 for saying why, because they have the same refractive index, or light travels at the same speed through each, so therefore the light does not bend. So returning to my questions, what is the maximum power of the eye? Well, you see, the cornea is no longer part of the lens system. The cornea is no longer doing a job of bending the light when you're underwater. So therefore, the only part of the eye that acts as a lens is your variable lens. And what is its maximum power? Well, we've already done this earlier. If you remove the cornea from the lens system, well, you're only left with your variable lens. And we saw that earlier. That was 26 per meter. That is your the maximum power of the eye now, because it just depends on the variable lens. Next part. Why do objects appear blurred? Why can't I properly focus? Look, there's a mathematical calculation where we work out the object distance in the notes, and we get a negative value. Now, you don't have to go into that kind of detail, but all we're basically saying here is, why does it appear blurred? It appears blurred because the lens is not powerful enough to focus the lens on the retina. My maximum power is 26 per meter. The retina is 2 centimeters behind. So no matter what I do, I can't find a real image on the retina. You can do the mathematical calculation if you wish, but that's probably too much detail because we're only talking about 3 marks here. Then the final part is, explain why wearing goggles allows objects to be seen clearly. Well, just the fact that she's wearing goggles means there's now a layer of air between her and the cornea. So when the light goes from the air into her cornea, the cornea can now act as that lens. So for 5 marks, what will we say? We will say, wearing goggles, the light refracts from air to your cornea. That layer of air inside your goggles is now important. The cornea now acts as a lens. The cornea is now brought back into play by having that layer of air in front of it. That was a good question. Tough question.